I don't mean that the laws of physics exist or that they are precise and mathematical. I mean the fact that an animal whose closest relative is the chimpanzee was able to ask about these laws, there he is up there, but was also able to navigate through a sea of wrong ideas and eventually hit on relativity, quantum mechanics, the standard model of elementary particles, and more. That is an absolutely remarkable fact that is not a physics fact, it's probably a biology fact, but it just blows me away. What are the tools that our ancestors used, intellectual ancestors? I don't mean the monkeys. I mean Newton, Einstein, and so forth. What were the tools that they used to be able to answer these questions? Well, there were theoretical tools, thought experiments, apparent conflicts of principle, paradoxes, and of course, mathematics. But some people would say the most important tool was, of course, experiment. Today, we're going to talk about a subject, quantum gravity, which is so remote, the scales of distance so infinitesimal, the energy so enormous, that direct experiment is entirely out of the question, at least for now. They're the phenomena which are at the intersection of quantum mechanics and gravity. Quantum gravity, to give it a name. So we theorists are on our own. Can we make progress? Well, it seems that we have made serious progress over the last 2 decades, maybe even revolutionary progress. Okay, as I said, the phenomena are so remote that the possibility of experiments is out of the question, and it means we're really on our own. We have made progress, and I'm going to tell you some of the little pieces. I'm not going to give you the whole story, I couldn't possibly, but I'm going to try to give you some feel for what some of the pieces have been that I think are adding up to a revolution. Okay, so where are we? The whole subject of quantum gravity probably goes back to the first day that anybody thought about quantum mechanics and thought about gravity. But the modern era of it, I think, started in 1958 or sometime around then, when theoretical physicists asked the question, should we quantize gravity? Now, what does quantize mean? Quantize was an expression which meant a procedure that you do on a classical system. The classical system could be a harmonic oscillator, it could be an atom, it could be electrodynamics, ordinary electrodynamics. A procedure which, if you know about that procedure, you recognize the equations. If not, it doesn't matter, there are equations. And the founders of the subject, Paul Dirac, Feynman, DeWitt, Weinberg, Wheeler, Hawking, their attempts were organized around trying to describe scattering processes, processes where particles come in and particles go out. They interact under the influence of gravity, and here and there they may emit some gravitational waves, gravitons. They invented Feynman diagrams for gravitation. Well, it was a disaster. It was a disaster. Everything they tried to compute came out infinite, or came out meaningless, came out nonsensical. And that led to what I would call an era of angst and confusion, a time when it just did not look as if quantum mechanics and gravity were compatible. Now, how could they not be compatible? They have to be compatible. The world has both, and we can't live in a world of inconsistency. And that was then. How do you fit them together? Can you fit them together? And it looked impossible. Today, the situation is different. Today, as far as we can tell, not only can gravity and quantum mechanics fit together, but it's almost as if they were the same thing, or two sides of a coin, a single coin. I'm going to tell you a little bit about some of the things that went into that. All right, I always start with digressions. I'm a great digressor. I digress all the time. I'm going to digress about something you've all seen, holograms. What is a hologram? You've probably all seen them. The first holograms were something like this. You had a region inside a cavity of some sort. And the cavity was not a cavity, just a round region. And the cavity, the surface of the cavity, was a film, a photographic film. And if you looked carefully at that film, even through a microscope, all you would see was little scratchy, meaningless rubbish, noise. It seemed to encode nothing, nothing recognizable. On the other hand, if you shined light on it of the right kind, what is called coherent light, all of a sudden, voila, an image would form, but a three-dimensional image right in the middle of this cavity, a three-dimensional image of whatever it was that had been photographed. What is a hologram? From an abstract point of view, a hologram is a two-dimensional mathematical representation of a three-dimensional portion of the world. Now, how do you manage to take a three-dimensional thing and map it into two dimensions? Well, it's possible, but it is always at the cost of the two-dimensional image looking like a random hash. How you put it back together again, that may be just shining light on it, or it may be some much more complicated mathematical procedure. But that's what a hologram is. And what you can say about a hologram is that things are not where you think they are in the hologram. The information, let's call it the information of what is in the hologram is in the film. The image is in the bulk, what we today call the bulk. Things, or the information encoding things, are not where you think they are. I want you to keep that in mind. Now, let's come back to quantum gravity. In the 1990s, this was the period when Stephen Hawking and I were having our fun debating, and Raphael was a student. Thought experiments, principally initiated by Stephen himself, about black holes led to something called the holographic principle. What was the holographic principle, and what is the holographic principle today? It's the idea that a region of space with everything in it, it could be astronomical space, it could just be this room, or even the whole universe, that the information encoding everything taking place in this three-dimensional world is encoded on the boundary of that region as a kind of quantum hologram. It's of course impossible for me to describe the mathematics of the quantum hologram here, I won't try, but that's the message. And again, things are not where you think they are, or at least things are not where the information which is encoding them would lead you to believe they are. Okay, let's come back now to this idea that gravity and quantum mechanics may be so closely related that they really are just two sides of the same coin. The evidence for that is a whole bunch of parallels between gravitational phenomena, we'll talk about what that means in a moment, and quantum phenomena, things that we had no idea were connected. Things from two radically different fields of physics are turning out to be parallel to each other and perhaps even not just related to each other, but the same thing. The connection is through this holographic principle. The gravitational phenomena are the phenomena which are like the image, the three-dimensional image. The encoding of that three-dimensional world is in the form of the quantum mechanical hologram. The correspondences are correspondences between the two of these. So I will give you some examples. Let's go to the most primitive or basic of gravitational phenomena. You all know what that is. If you've fallen out of bed, I've fallen out of bed a number of times, regularly. You know what gravitation is. It's falling in a gravitational field. And if I wanted to express it abstractly, I would say that the gravitational force, just like any other force, is a tendency for things to accelerate. In this picture here, the apple is accelerating. It's accelerating downward, caused by the gravitational field of the Earth. You can rewrite, the equation F equals ma, of course, you can rewrite that as F equals the rate of change of momentum. The momentum of the apple is increasing as it falls. So you can say that falling is the tendency for momentum to increase in the presence of a gravitational field. That's one side of the coin, the falling side. The other side of the coin, the quantum side, is something so radically different that it's hard to imagine that it has anything to do with it. You take some quantum system. Now, this quantum system I'm imagining is the quantum system encoding the hologram. This bunch of squiggles and random-looking bits of information out at the boundary of the region of interest. And you come along and you tap the system, you perturb the system. You might hit it with an extra electron, or you might do whatever it is that you do to it at some spot. You perturb the system. That perturbation, this is a quantum mechanical fact, will start to spread throughout the system. Its influence will spread throughout the system like an epidemic. You touch one qubit, if you know what a qubit is, that qubit will touch a few more qubits will touch a few more qubits, and the effect of perturbing the system will spread. There's a notion of size. It's like the size of an epidemic. The size of an epidemic simply means the number of sick people. And the number of sick people has a tendency to grow. Here's an example for the experts on quantum computation. There's a quantum circuit, and it proceeds from left to right. If you perturb it with a green qubit, that perturbation will spread throughout the quantum computer, and that's the phenomena of scrambling, of information scrambling. Now, what on earth does this have to do with falling? I'll give you an example. It comes from a setup called ADS-CFT that may not mean anything to you. It's fine, it doesn't matter. What is this? This is the boundary far away, the boundary encoding the hologram. The bulk of space, the interior, is in here. Imagine coming and perturbing the hologram. Perturbing means just hitting it or something. That information that you've done so starts to spread. It starts to spread throughout the hologram. And there is this notion of the size of the perturbation. You can calculate these things, and the calculation, as I said, is purely quantum mechanical. Maybe a bit of quantum field theory, but no gravity. And what do you find? You find that the rate of change of size in this setup is exactly equal to the mass of an object which was created at this point times the gravitational acceleration. These quantities here you get from elsewhere, but they're well defined in the context. And what does it say? Well, what would gravity say? Gravity would say that the time derivative of the momentum of the particle that's falling is equal to mg. And so we see these two different fields of physics, entirely different, coming together and giving rise to an equation. I don't know if Galileo would have recognized it in quite this form, but it was Galileo's equation. And in order to make sense of it, you have to believe that momentum of the object which was created is simply the size of the perturbation. Now, you may not understand that. You may say he's talking gobbledygook. And the main thing that I want you to get from this is, again, this correspondence between gravitational things, this unexpected correspondence between gravitational things and quantum things. Here's another example. Instead of a flat plane being the hologram, we can imagine the hologram as a sphere surrounding some place. At the center of the diagram, the center of the picture, there might be a black hole or planet or other mass. If you do the same calculation in this context of calculating how the size of a perturbation grows, again, purely quantum mechanically, what do you find? You find the marvelous formula that the rate of change of the size, the mass times the acceleration of the infalling object, is just equal to the product of the two masses, Newton's constant, and the distance between them squared. In other words, Newton's law of gravity. Quantum mechanics, the growth of size. Gravitation, gravitational attraction. To me, that is very stunning correspondence.